Let's talk our way through problem 22 in section 8.2, that's page 254 of Hungerford's undergraduate abstract algebra book. So, if F from the group G to the group H is a surjective homomorphism of groups, and if N is a normal subgroup of the domain G, prove that F of N is a normal subgroup of H. So, the first real work we have is we have to think through all of the pieces of that. So let F from G to H be a surjective or onto homomorphism. Okay, what does that mean? That means that so you should be sort of thinking off in your head there. Maybe we'll put some notes off to the side. That means F of, we'll say AB just for the fun of it. F of AB equals F of A, which is an element in H, times F of B, another element in H. That's homomorphism. We also know for all, let's say H in H, there exists A in G such that F of A equals G. Okay, so it's really important to think about what you have, sort of get these facts oriented, then you can play with sort of maximum power. Okay, we'll let N be normal in G. Now, what you should really sort of plan A there is AN equals NA. That's the definition of normality for all A in G. But you should recognize with theorem 8.11, okay, that we have a bunch of other forms that are equivalent to this. So we can use those here. They're at our disposal, okay? Now, what we want to show, okay, that F of N is normal in H. Now, remember, F of N, that's the set of F of A such that A is in the domain. Oh, sorry, A is in N. Sound good? So, all of those things are normal in there. Okay? So, what does it mean to show something is normal? Well, let's think about that. If that's what I want to show, I have to think about this. Now, in theorem 8.11, I have my favorite approach, which is part 3 there. So as long as I can show that A, N, A inverse is in my normal subgroup for all A, life is good. Okay. Now, I've used A a little differently than there. So now I'm showing something is normal in H, okay? So I'm going to say let H, okay, be an element of capital H. And what is my element going to look like in here? And, well, let's just go ahead and call an element, I don't know, Y, be an element of F of N. We want to show that H, Y, H inverse is in F of N by theorem 8.11. This will show Fn is normal in H. Okay, so make sure you believe that that's sufficient by part 3 of theorem 8.11. Okay, so I have these two elements. Let's think about the consequences here. Again, these are the things I'm going to use. So I'm somehow, these things all sit in H. You can bet what's going to happen is I'm going to somehow pull them back over to this direction. Okay, so since this is onto, since F is onto, choose A in G such that f of A equals G, and by definition, of Fn, choose n in N such that f of n equals y. Now some people would actually just call this element f of n to start with, but I went ahead and picked an element that's in that set, and then by definition of being in that set, it says, hey, there's something in the normal subgroup that maps to it. So I have these pieces, okay? Now don't forget what I want to show. I want to show that that is in f of n. Well, what does it mean to show that something is in f of n? I need to show that f of an element in n is equal to that. Well, what is that? H, y, H inverse. Well, H is equal to f of A, y is equal to f of n, and H inverse is equal to f of A inverse. Remember, that's a property of homomorphisms. Okay, since this is a homomorphism, I can put these two things together. You could do this in two steps and say f of A n and then put this in. I'll go ahead and use the homomorphism property twice. F of A n A inverse. Okay? But, well, what's the whole point of having n? Well, n is normal. N is normal in G, so A n A inverse is in n, right? Therefore, this is equal to an element of n mapped by f. Therefore, H, y, H inverse is in f of n. And there you have it.